Okay, thank you for joining today. I'm Adam Dello. I'm a technical sales representative for Thermo-Kinetics. And the mission for today is to both introduce you to Thermo-Kinetics if you're not already familiar with us, and then share with you some best case or some applications on how to get around some of the inherent issues that are present in thermocouples. So the agenda today, like I said, I'll kind of give you a bit of an introduction to Thermo-Kinetics and who we are. And then I'll also go through how important is product fit and quality for you. We'll take a look at thermocouples and their applications. We're also going to take a quick look at RTDs and some comparisons to thermocouples. We're going to take a look at selecting the right product for your application and ensuring your measurements are accurate. That kind of goes hand in hand with selecting the right product. Like I said, I'll have a bit of a section for questions, and then I will just summarize, and hopefully we'll keep it nice and tight between 20 and 25 minutes. So, Thermo-Kinetics, measurement and control. My grandfather actually started the company back in 1971. We are present in the steel, oil and gas, chemical, and other heavy industries as well. Basically, anywhere we see a high temperature, that's where we are present. So the company, like I said, my grandfather started it out of his garage, mostly focused on thermocouples and RTDs. So we're still manufactured in Mississauga, our thermocouples and RTDs, as well as some of our protection tubes and thermal wells as well. With all of that time in the industry, we have a wealth of knowledge of in-house expertise that helps you find the right solution for your application, whether that's selecting the right thermocouple calibration type, the right RTD, the right protection tube, or a variety of other solutions as well. Before I really get into too much on the thermocouples, just a quick introduction on who Thermo-Kinetics is outside of the thermocouples. So on top of thermocouples in our manufactured product, we also have a line, multiple lines of very high quality and high accuracy solutions for the process control industry. These include Honeywell. We've been with Honeywell for quite some time, carrying either their fixed gas detection systems, their field instrumentation, or their process instrumentation. So whether that is level, pressure, temperature, contact or non-contact, wireless solutions, dissolved oxygen, or other analytical systems as well. Simple temperature controllers like the UDC pictured there, and then all the way up to PLCs and smaller level DCS systems as well. For our non-contact and infrared measurement pyrometers and imagers, we have LumiSense. And once again, they can be as simple as simple point and shoot pyrometers to boiler inspection systems, to sulfur recovery unit monitoring systems, or flare stack monitors as well. And then even going to the point of vessel monitoring with thermal imaging equipment as well. For any type of electric heating applications, we have Control Concepts, who makes a very high quality SCR that can be either controlled through Modbus, TCP, Ethernet IP, or other process control networks. I'd be happy to talk to you a little bit more in detail about that. On top of that, not to go unsaid, we have Krona for flow, HANA or Hawk for ultrasonic non-contact measurement, also Precision Digital, RioTemp, Lennox, and EPI. As a part of all of these webinars, I'm going to try to include upcoming webinars and focus on either specific applications with these or specific case studies as well. If you do have any requests, feel free to pass those along to me and I'll make sure to make those a priority. So the reason why we're all here is to talk about thermocouples and their applications. So most likely in the industry that we're in, if you're joining in on this webinar, you're most likely familiar about what a thermocouple is. But it might be worthwhile for us to just go in a little bit more detail so we can understand a little bit more about what we're talking about. So thermocouples come in a variety of shapes and sizes, but generally they are two dissimilar metals joined together at one end, sometimes exposed, sometimes insulated, either in a stainless steel tube or a ceramic tube. And basically these two dissimilar metals between the hot junction, which you can see here, and the cold reference junction, you're actually getting a millivoltage output, which allows you to make a calculation of what that hot junction temperature is. There are typically about 8 main thermocouple types or calibrations, covering temperature ranges up to about 1700 degrees C. These are pretty standard across the industry. On the right of this screen here, you can see some of the different calibration types and some of their typical color coding applications as well. So for J and K, or J is typically a white for the positive leg and red for the negative leg. Just one thing here while I have the video up, and I do have some samples in front of me here. If you ever are in a situation where you're looking at a thermocouple and you're not exactly sure which one it is, either the lead wire has lost color or you're not exactly sure which one it is, for a J type, the positive leg is white and the negative leg is red. The positive leg on a J type is magnetic, while if you were looking at a K, the negative or the red would be magnetic. So if you've lost a little bit of color in the yellow on your K and you're not exactly sure if it's a K or a J, that's a quick simple test. Is the positive white leg on the J is magnetic, while the negative red leg on a K is magnetic. That's just a quick simple test there for you. Going a little bit more detail about the actual applications of these different types of calibrations. J types are pretty much the most consistent or low temperature applications that you're going to see. Quick and dirty thermocouple, normally used in the plastics industry, can use to be about 800. We have it listed here on ours as 760 degrees C. One issue with these is that they are subject to rusting on the iron leg of the J type. K is what you're going to be seeing most prevalently. I'm going to talk about that in just a little bit. T is a copper constant hand thermocouple that's used in lower temperatures, so sub-zero temperatures is where you're going to be using T, whether that's often used in either agriculture or cryogenics as well. For a type E, these are a little bit newer breed, but they're developed to solve some of the problems with J and K type. That has a higher millivoltage output per degree and can be used up to about 900 degrees and has a little bit more linear output curve compared to some J and Ks as well. And then also in comparison to the J, it's not subject to the same rotting leg or rusting leg that the J is as well. So K types, like I said, are probably the most consistently used in the industry today. Probably what you've mostly seen, normally up to about 11,000 or 1,000 or 1,200 degrees C, used in the steel, glass, petrochemical, ceramic industries. This is the most kind of bang for your buck of high temperature and low cost here. When we get into really high temperatures, that's when we start looking into the platinum elements. So we're either looking at R and S. These are a combination of platinum and rhodium thermocouples. We're getting up to about 1,600 degrees C, and we can even take it a next step up with a B-type thermocouple and up to 700 or 1,700 degrees C. So I did mention a little bit about K, but I'd like to, since it is the most prevalent, I'd like to talk to a little bit more detail about some of the issues that are existing in K. I thought I was actually going to talk about that, but I forgot I have an extra slide on RTDs for you. So before we get into Ks, I just wanted to kind of give you a comparison about thermocouples and RTDs. So RTDs, you may be wondering where they're applied, where they're best used. I'll just give you a brief intro and then help you make a decision on when you should be using RTDs and when you should be using thermocouples. So RTDs measure the temperature by measuring the actual changing resistance of a metal. The metal within the RTD bulb is a platinum, normally a platinum wire as well. They are specified according to their resistance in ohms. So a PT100 has a resistance of 100 ohms at 0 degrees C. RTDs, they come in multiple wire configurations as well, either 2, 3, or 4 wire configurations. In these, like I said, platinum wire is what is actually used to measure the resistance change in the bulb of the RTD, while the extension lead wire is copper. In a two-wire RTD operation, it's actually sometimes difficult to compensate for the actual resistance change for the copper. So that is why we normally would recommend using either a third or fourth wire RTD so that you can compensate the resistance of those copper legs and understand more accurately the temperature that the RTD is reading. So just main thing to pull out from this screen, if you are using RTD, whenever available, please use a third wire. You're going to get a lot more accurate reading with it. So when are you actually going to make that decision between a thermocouple and an RTD? So RTDs, their temperature ranges are about -200 to 650 degrees C, while thermocouples are 0 to 1700 degrees C. So right there, if you're going below 0, RTD is going to be a great selection for you. When it comes to accuracy, RTDs are normally a lot more accurate, 0.1 to 1 degrees C, while thermocouples a little bit more variance, especially once you start getting to those higher ranges. You normally change away from just a decimal value of error as opposed to a percentage of the actual measuring range that you're reading. So accuracy of RTDs, if you really need a very accurate measurement, RTDs, and you're within their 650 degree range, then you normally want to go with an RTDs. One thing that thermocouples really excel at are both their industrial application, so higher level temperatures and more resistance to vibration, but also a higher and a faster response time. RTDs have a pretty slow response time, about 1 to 50 seconds on a step change, while thermocouples are a lot faster, 0.1 to 10 seconds on a step change. We have a lot more information in some of our catalogs as well, or if you have any questions specifically about response time, especially when you're using a thermal well or some protection tubes, best to call into Thermo-Kinetics, either myself or our inside sales team. We'll be able to help you select the right thermocouple and the right probe for your application. As I mentioned earlier, I wanted to get into now the inherent issues with K-type thermocouples. So one main issue with the K-type thermocouples is that the chromel wire is subject to oxidation and green rot. It's actually also found, so the actual chromel leg oxidizes, gets that green rot. You either get that green coloration, you start building grain growth within the actual element. You will start to see a temperature measurement drift low, and eventually there'll be a mechanical failure where the actual leg will become so brittle it will crack. There's some different things that lead to that. It can be either a reducing or an oxidizing environment from the actual furnace itself, but it's also found that some standard steel sheaths, either 310, 321, 304, 316, and Inconel as well, they also contain manganese, and this migrates through the insulation, which you can see on the thermocouple here, and further contaminates the conductors as well. Especially at those higher temperatures, that's when you start to have the steel tube actually become more porous, allowing more of the furnace atmosphere in, as well as start to let off some of those off gases like the manganese. Another serious problem once you start getting to those higher temperatures and cycling with those higher temperatures is the differing expansion coefficient between the conductor and then the sheath material as well. And then one last thing that's causing a lot of issues in K-type thermocouples is sulfuric atmospheres will attack the element as well. This will cause rapid embrittlement on the thermocouple and then eventually lead to breakage of the negative leg. There can also be an issue of not having enough space within your protection tube as well. So that's something to be aware of as well. If you're inserting a thermocouple into a protection tube or a thermal well, being aware of how much outside space is available around the actual thermocouple to allow actually air to flow, and you're not just getting an oxidizing or a reducing environment right on the thermocouple as well. So some solutions that we can take to look at is either shortening the thermocouple or the tube, We can select, like I said, a larger outside diameter protection tube, resulting in a larger inside diameter as well, giving a little bit more space for the thermocouple to breathe. We can look at purging the tube with clean air. One other thing that you can do as well is actually add an additional sacrificial titanium wire within the protection tube as well. What this does is that the environment would actually more prevalently attack the titanium wire as opposed to the chromel leg of the K-type thermocouple. So you're basically just adding a sacrificial lamp into the thermocouple or into the protection tube with it so that the titanium wire is first attacked, and you can be replacing that as opposed to the K. And then one thing that I've been seeing a lot in customers is, especially when you're within that 850 degrees C to 1200 degrees C, and you're cycling a lot within those temperature ranges, there's a lot of steel, either Inconel or 316 stainless steel, being used in furnaces like that. And over time, those protection tubes are degrading, and more seeing higher levels of green rot, and that green rot occurring faster as well. What I've been working with some of my customers on is replacing some of those Inconel and stainless steel protection tubes with either a mullite or alumina or different ceramic protection tubes as well. What this actually solves is these are, especially when it comes to mullite is a 99.7% pure protection tube or ceramic protection tube, which will greatly reduce the number of off gases that the manganese off gases that the steel is giving off. And another thing is they're non-porous protection tubes as well, so you're not exposing the thermocouple to the atmosphere as you were with either a steel protection tube and when you started to have some more crack within the actual metal because of the expansion of the metal as well. So those are some issues some ways that you can attack some of the issues with K-type thermocouples. There is another way that you can go about this though, and this would be with the N-type thermocouple. The N-type thermocouple is normally referenced as an enhanced K-type thermocouple. They go a long way in actually solving some of those issues that we talked about on the last slide. The absence of aluminum and manganese in the negative conductor actually increases the stability of N over a longer period of time. So even going further and above some of the oxidation issues that we saw in the last slide, the N is actually, like I said, a more stable product for a longer period of time. Also, the extra silicon and magnesium in the negative leg actually offer another barrier of magnesium to protect it from the rapid oxidation as well. So to combat some of these problems with thermal expansion, there's actually a new sheath that was developed directly for the N-type thermocouples. This is called Pyrosil D. This has very similar metallurgical properties as an N-type thermocouple's legs. So you see a very similar expansion rate on these N-type thermocouples to the Pyrosil D MgO thermocouples. Excuse me. And then one last thing with the Pyrosil D is these can be used at a higher temperature as well. They can be used at a slightly higher temperature than K-type. So while you also get the expanded or less drift with an N-type thermocouple, higher resistance to those oxidizing environments, you can also measure a slightly higher temperature than a K-type as well. And what this does for you or your customers is that it allows you to measure that higher temperature that maybe a K might not be able to measure without having to make that last jump up to a platinum R or S thermocouple when you start to see a very large jump in price as well. That is kind of about it when it comes to N-type thermocouples. But that's not it when it comes to some of the other errors that you can be introducing into your measurement by using a thermocouple. So some of the other things that you can start to see is poor location. So that's either if the thermocouple is in either a dead spot of the furnace and maybe directly in front of the flame and cannot get a true reading of what's actually going on in the furnace. So that's the first thing to be aware of when you're installing a thermocouple or you're selecting a place to be putting this thermocouple into the environment. Where is it actually going to be located? Number two that can be a source of error is sagging. Try to install a thermocouple vertically whenever possible within a furnace. Horizontally over time at high temperature, obviously that protection tube in the thermocouple will start to sag, which can lead to either mechanical breakage or make it a lot more difficult to remove as well. One thing to be aware of is induced voltage that thermocouples can experience. So try to keep them away from electric motors, high voltage wires, and other high areas where you might see an induced voltage. Try not to handle the thermocouples as well. Try not to handle the thermocouples. Some incorrect handling can lead to further sources of error down the road. Handling can either break a fragile wire in a platinum or in a very small thermocouple. And also, if you are moving them, making sure that they are inserted at the same depth that they originally were installed as well. You don't want to start inducing some error by installing the thermocouple at differing depths at different times as well. One thing to be aware of, and I see this actually more commonly than you might think, is the incorrect insertion depth of a thermocouple into a furnace. So very often you will see a thermocouple that is installed only slightly into the wall of the furnace, and then there's either some refractory or some sort of type of insulation. The general rule of thumb is about 8 to 10 times the diameter of the actual thermocouple or the thermowell or the protection tube to be inserted into the furnace. And so what that's actually can prevent is the insulated side of the protection tube or the thermocouple being a heat sink and actually sinking a lot of the actual furnace temperature away down into the actual tube, resulting in a lower measured temperature than actual temperature as well. So like I said, incorrect insertion depth can be a major issue. One thing to combat that is 8 to 10 times the diameter of the actual protection tube or thermowell inserted into the process. Choosing the largest thermocouple possible, and that actually means being the diameter of the thermocouple, will actually offer a longer lifetime. We have some charts in our brochures as well for this. You will get higher temperature ranges for your thermocouples based on a thicker diameter as well. This will also increase more insulation between your elements and the outside atmosphere as well. So it's just going to result in a longer living thermocouple as well. Contamination is something to be obviously aware of. We mentioned that a lot when it came to oxidizing and reducing environments. So just being aware about the atmosphere that your furnace is putting your thermocouple under, and either looking into different protection tubes to protect your thermocouple or purging the protection tube to further protect the thermocouple. And then one thing that is a source of error and something to be aware of is time drift. So all thermocouples drift with time, especially K though. The drift is directly proportional to cycling. So this is something to be aware of when you are cycling a thermocouple. The magnitude as well as the number of cycles will cause drift to occur more frequently and make it worse. If you are unaware of how cycling is affecting your thermocouples, there is a standard for the automotive industry as well, or there's a standard for the automotive and the aerospace industries. For the aerospace industry, this is AMS 2750. The current revision is E, and they'll be moving to F eventually. They have some calibration and some lifetime recommendations within those for the specific industries. Those include also calibrated thermocouples, but those can also be, if you are cycling at high temperatures, can be a pretty good rule of thumb of when you can expect to see thermocouples need to be replaced due to time drift and due to high temperature cycling as well. Like I said, send me a message or send me an email and I'd be happy to kind of send you in the direction for those standards. Those are a pretty good rule of thumb of trying to figure out when you need to be replacing your thermocouples based off of time drift. So that's kind of about it for applications. One thing that I wanted to mention to you is our ISO accredited lab. So our lab at our office in Mississauga, we are capable of calibrating various sensors, either thermocouples and RTDs, pyrometers, and field instrumentation. We are an ISO 17025 accredited lab. And what that actually is actually a metrology standard and not necessarily just a standard industrial standard. So we have a very high accuracy, very high temperature applications as well. So either a pyrometer or any types of thermocouples, especially if, like I said, if you are working in the automotive or the aerospace industries, we have a full capability of calibrating and providing you with certified thermocouples as well. We also have the capability of repairing various process solutions, either temperature controllers, pyrometers, or field instrumentation as well. I would just offer that you reach out to me about something that you're looking to have repaired or calibrated, and I'd be happy to respond to you of our capabilities in actually calibrating or repairing that unit. So at this time, I'll just jump out here and see if I had any questions in the group here. I don't see any questions. Is there, oh, 2 questions. Here we go, Raphael. Get my notebook here. So Raphael's question is, where is the Pyrosil D with respect to the sensing element? Okay, that's actually a great question. So the Pyrosil D is actually, so for the most part, especially on the K-type, I was talking about bare element thermocouples. So the bare element thermocouple with the insulation material that you'd put into a well itself. For the Pyrosil D, it is actually the sheath for an MgO material. So MgO actually has the 2 legs within the sheath here in a metallic sheath. There's magnesium oxide used to insulate the actual elements, and then the sheath itself on the outside is where the Pyrosil D would be found. So if this was an N-type, you would have your N-type elements within here, MgO to insulate, and then the Pyrosil D would be the sheath instead of a 316 stainless steel is normally where you would see this sheath. So that actually sheath and the thermocouple would be expanding at the same time. And the second question from Raphael was, how many cycles would you recommend for replacing and recalibrating? I assume cycling would be a cool down, i.e. shutdown and startup. That is a more difficult question to answer, unfortunately. You kind of have to take a look at it on a case per case basis. It kind of depends on where you're cycling as well, like the temperature ranges that you're cycling at, as well as the frequency that you're cycling at as well. And then as well, the error that you're willing to accept within your process as well. So as I mentioned, the aerospace industry has a lot of standards, very high standards. The AMS 2750E, AMS 2750E, that is a pretty good rule of thumb. Obviously, it's a little bit overkill, especially if you're not in the aerospace industry. There is also an automotive industry standard as well that's starting to come out as there's a higher level of quality expected out some of these automotive tier 1 and tier 2 suppliers. Off the top of my head, I believe, and I may have to be corrected, that it is CIQ9. Those both have very good recommendations for that. If you have an idea of the process that you're looking at, though, if you can share those details to me, I'd be happy to answer with you. The best rule of thumb, though, especially if you have a lot of repeatable thermocouples within your process, what I've been recommending to customers, if they are looking for that recommendation of when they should be replacing and recalibrating thermocouples, that is a difficult answer to say, but one thing you can do is purchase a calibrated test source thermocouple that you replace once a year. So that would come with documentation that it is a calibrated thermocouple that you can be using to reference that actual thermocouple. So you can start to build a bit of a PM with some of the math involved in like a document like AMS 2750E. You can build in like a PM of when you should be replacing it, and then with a source calibrated thermocouple, use that to actually validate the actual measurement that you're getting from that thermocouple by inserting it into your process and comparing it against what you are reading. Okay, so Raphael asked another follow-up question. What would be a delta that you'd consider cycling? So turning down and starting up versus full shutdown for maintenance. Again, that's a little bit more difficult to state, but those are actually sometimes mentioned within the AMS standard as well. Normally, when you start to talk about a lot like heavy green rot on the actual K-type thermocouples, normally it's above 850 and below is less than a delta per se, but above 850 and below and cycling back and forth is really where you start to see green rot in those applications. But in that AMS standard as well, there's actually two different types of recommendations based off of the temperature ranges that you're in. I can't remember the exact ranges, but there's one that's within a couple like 300 degrees C and 0, and then there's another one that's that flickering over that 850 degree line. I'm not sure. I don't think that was an exact answer from you. I can follow up with you and send some more exact information in an email. That off the top of my head. The delta is a little bit harder to really nail down. It looks like Raphael's got another question here. Okay, so yeah, it looks like Raphael's looking into some replacement schedules for some customers. So I will, as a follow-up to this as well, I will, for anybody who attended, I'll be sending out, I'll send out a PDF of the presentation. I'll also send you a recording, and then I'll also send you some information about AMS 2750E and CIQ 9. And then Raphael, I will reach out to you directly as well and start a conversation about looking into those replacement schedules for your customers as well. Does anybody else have any other questions? Okay, well, we're a couple of minutes over our scheduled time, so I really appreciate you guys taking the time to join me today. As we kind of start to look into this start to mold into this new world this week and see what it's going to look like. I'm assuming we're going to do a lot more of these. I appreciate you guys coming in and sitting in on this thermocouple application. I will be bringing in other of our solution providers like Honeywell, like Precision Digital, like Lumisense to be providing presentations similar to this. If you have any requests at all, feel free to either send me an instant message, send me an email, and I'll be happy to share some more information about you and listen to your requests and schedule another webinar that's fitting to your requests as well. So thanks again. Thanks for joining. Stay safe, everybody, and have a nice day.